So class, welcome to the lecture number 18th of the course PSOC. Okay, so this is unit third, I think fourth lecture of unit third, subject at PSOC, power system operation and control. Okay, so if you remember in the previous lecture, that is lecture number 17th, we derived an equation for the moment of point for us for the displacement of point E, okay, from its nominal value, okay, and the displacement was given by delta xes. So this delta xes is the displacement of the point E. If we want to increase the turbine output by small amount, okay, using a speed changer, okay. So the equation was given as k1 k3 delta pc s. This is the change in the position of the power corresponding to the change in the position of point A because of the speed changer, minus k3 k2 delta fs. So because of the change there will be some frequency deviation as well, and this was k4 plus s divided by k5. So you know how on which factor these these constants k1 k2 k3 k4 and k5 depends. Okay, it depends upon the length of the linkage mechanism. It also depends upon the proportionality constants, like where we were taking the integral of the where we were integrating it, and where we are using certain other proportionality constants. Okay, so if I was representing the whole equation in terms of delta xcs as delta PCS minus 1 by R delta Fs. So what was left? It was left was KSG divided by 1 plus STSG, where KSG was the constant of this small g means governor. Okay, don't get confused. Don't never represent this small g as generator. This small g is the governor. Okay, so where R1 was equal to K1 by K2, which is nothing but the speed regulation of governor. Speed regulation of governor. Okay, and what was KSG? KSG was nothing but K1 K3 by K4, which was gain of the speed governor. Gain of speed governor, and TSG was nothing but time constant of speed governor, which was equal to 1 divided by K4 K5, which was nothing but time constant of speed governor. Okay, so these were the means this is how this equation was represented. Okay, so I'm supposed saying this equation is equation number x. Okay, so if you will see, if you will draw a block diagram corresponding to equation number C, where delta xes is the output, okay, which is the moment of the point E, and what is the input? Input is the delta PCS minus 1 upon R delta Fs. Okay, so the how the equation is, how this equation is represented in terms of a block diagram. Firstly, we will represent the block diagram by this function. Governor block is represented by this function KSG divided by 1 plus S TSG. This is the governor. This is the output of the governor, which is nothing but delta XCS. Okay, the input to the governor, it was nothing but delta PCS minus 1 by R into delta Fs. So this was how this equation was represented in terms of the block diagram. So net input to this to the governor, if you will see the net input to the speed governor, this is speed governor. So the net input to the speed governor is delta PC minus 1 by R into delta Fs, and delta XCS is the output of the governor. Okay, so I am saying delta PC minus delta Fs by R, it is in Laplace domain, so it is the net input. And what is the output? Delta XC is the output. Got it? No, what we are not interested in the turbine valve position. Okay, we are not actually interested in the turbine valve position. So what we are interested in, what we are interested in the change in the generator output. Okay, we will see if there is some change. Because of that change in the system, the generator output will change. Okay, we are interested in that change in generator output, or incremental generator output, change in incremental generator output power. Okay, so what I'm saying that we are not interested in the turbine valve position, but in the generator power incremental. Okay, so I'm saying, suppose I'm saying, because of the change in valve position, okay, because of the change in valve position by delta XE, okay, so because of the change in valve position by delta XE, it causes a change or increase in the turbine power by delta PG. No, this capital PG is the G is the generator. So I am saying, because of the change in position of point X by delta, change in position of point E by delta X E, the output of the generator will change by delta PG. Okay, so uh, basically, if you will see, this turbine is not directly connected to generator. If I will draw a diagram, I will show you. Suppose this is my fuel. This fuel, it can be coal or water, whatever. If it is a thermal power plant, it is coal. Okay, and if it is hydro, it is water. Okay, but we are mainly concerned with the thermal power plant, because we are talking about the steam valves. Okay, so the fuel will be this coal, because we are burning coal plus water. Okay, coal and water, not coal plus water, coal and water, because by burning the coal, we are heating the water and we are creating a steam in a boiler. So once the steam is created, okay, this steam, here we have steam. Okay, this steam, here what is this? This is steam valve. This is steam valve, and this steam will steam coming from the boiler, it is controlled with the help of steam valve. Means this steam valve will control how much steam is flowing, will flow from the boiler to the turbine. Then we will have turbine, because the steam is ultimately striking the turbine blades, and turbine shaft is connected to the generator. So here we will get, here we have generator. Okay, got it? So by controlling the steam valve, we can control the speed of the turbine. Got it? So what I am saying that by changing the steam valve position by delta XC, it causes the incremental increase in the turbine power first, delta PT. Okay, delta PT is the incremental increase in turbine power, and because of the increase in PT, the generator output also increases, power generated also increases by some small amount, that is delta PG. Okay, because you know that when this steam strikes the turbine starts rotating. So this turbine shaft is connected to the generator. So this generator also starts rotating. Okay, rotating part of the generator, it starts rotating. So because of the mechanical interactions that are undergoing in the generator, some power is generated. Okay, that is represented by PG, and change in power is represented by delta PG. Suppose we are saying that the losses in the generator, they are negligible, then delta PT is equal to delta PG by neglecting the losses. By neglecting the losses. Okay, so I am saying the generator incremental loss is neglected, then we will say that change in turbine power is equal to the change in the generator output. Okay, so in this case, presently we are assuming that the voltage remains constant. Okay, we are assuming that the voltage remain constant. So what we are doing, by assuming that the voltage remain constant, okay, at the generator terminals, so increment and analysis will give us a relatively simpler relation between delta XC and delta PG. Okay, I'm saying assuming that voltage remains constant, comma, okay, assuming that the voltage remains constant, comma, incremental analysis incremental analysis will give a simple dynamical relation between the change in position of point E and change in generation power out. Why I'm talking about the incremental analysis? You say when we were driving now this mathematical model for the governor, there we said that for a small, to increase the generator power by a small amount delta PC. Okay, we say to increase the small generator power by a small amount delta PC, point A is moved upwards, means small amount. So small amount means incremental changes. Okay, so I'm saying by assuming that the voltage remain constants, okay, incremental analysis will give a simple dynamic relation between the moment of point E and the governor and the change in generated output power. Okay, so this relation between delta XC and delta PG, it is given by a simple single transfer function block KT divided by 1 plus S TT. Okay, this is small t. K subscript T. So what is this? This block represents the turbine. So what is input to the turbine? Input to the turbine is nothing but the output of the governor block. So what is the governor? Here we have the governor KSG divided by 1 plus S. TSG output of the governor is delta XCS. And the input to the governor, you know what it is. It is one input is delta PCS positive and the another input is negative 1 by R delta Fs. Okay, so the output of the governor is the input to the turbine, that is delta XCS, and the output of the turbine is delta PT, which is equal to delta PG. This is capital T, turbine power. Okay, got it? You got it? So now this I am saying that turbine can be characterized by a single gain constant KT and time constant TT. Okay, by a single gain constant TT and time constant TT. Now this turbine, okay, it is a single stage non-reheat type turbine. We have two types of turbines, reheat type and non-reheat turbine. In non-reheat type means whatever steam is produced, that steam is allowed to strike the turbine. Okay, and then the steam is condensed back and converted into water. But however, in case of a this is non-reheat type turbine. In case of a reheat type turbine, we use, instead of one stage turbine, we use multi-stage turbines. Okay, so what we do at in a means high pressure, low temperature stage, this steam is extracted, it is then reheated or superheated, and it is again fed back to the low pressure and high temperature stage. Okay, so that type of turbine is called reheat type turbine. Okay, so this is a non-reheat type turbine I am talking about here. Okay, so you will see by here, by opening the steam valve, okay, the steam, if you will see the if I'm talking about the time constant here, TT, so this time constant of the turbine TT, it is typically of the range of 0.222 second. How much? 0.222 seconds. So that means if you are opening the steam valve, the steam will not strike the will not reach the turbine instantaneously. Okay, the steam will not reach the turbine instantaneously. Okay, this the time delay experienced experienced by the steam, okay, from means from moving to move from the steam valve to the turbine, okay, is of the order of, I can say, 2 seconds. Okay, so this time constant I am saying TT is equal to 2 seconds. It is because of the time constant that, or the delay that is experienced by the steam in the steam pipes. Okay, so here if I will solve delta PG, if I will say delta PG is what equal to, delta PG in Laplace is equal to nothing but KT into KSG. Okay, KT, actually it is KT divided by 1 plus S TT multiplied by delta XCS. Okay, but what is delta XCS we calculated here? Okay, so we can substitute the delta XCS from equation X in equation Y. Can we? Of course we can. So what will be delta PCS equal to? Delta PGS, delta PG will be equal to KSG KT divided by 1 plus S TT into 1 plus S TSG, because these two blocks are connected in series. So there, whatever is inside this block, it will get multiplied. Multiplied by whatever is the input. Input is delta PCS minus 1 by R delta FS. Got it? Okay. So in general, I can say that the response of the turbine response is low with the response time of several seconds, means at least 2 seconds. It has a response time of 2 seconds. So I can say that this response of the turbine block, it is low because time is of the order of 2 seconds. Okay, so generally I can say that it is obtained that the turbine response is low. Is low with the response time of several seconds, which is approximately equal to 2 seconds. Okay, so I am saying, what is this delta PGS? It is the commanded incremental. So this is the change in the, or incremental change in the generator power because of change in delta PCS, or change in incremental change in the incremental incremental change in generator output because of the incremental change in delta PC. So in steady state, you are getting delta PG equal to this. Okay, so if you will use steady state means using the final value theorem, where you will get delta PG. How will you get? If you will apply the delta final value theorem, what will you get? Final value theorem is PG, delta PG is equal to limit S approaches 0, S delta PGS, okay, when delta PCS is equal to 0. Okay, so if you will use this theorem, that is final value theorem, you will get delta PG is nothing but it is equal to KSG into KC into delta PC. Sorry, here only this much. Okay, so you will get, you don't have to memorize this thing, only you will say in steady state you will get delta PG is equal to this. In steady state, delta PG, change in generator power, is equal to this. So this was about the non-reheat type turbine. Means this whole expression is for the non-reheat type turbine. Okay, so in reheat type turbine, what are we doing in reheat type turbine? In reheat type turbine, we have a steam valve. I'm writing reheat type. Okay, reheat type turbine. We have a steam valve. After the steam valve, the first stage we have, which is high pressure. High pressure stage. So it is a high pressure. It will be a low temperature stage. Then we have another stage, which is a low pressure. So if in a system we have a high pressure stage, what we do, low temperature stage, we take a steam from here and then we take the heat from the boiler, that is flue gases. That heat is used to reheat this steam, up to superheated temperature. Then it is again fed back into the low pressure. The steam is fed into the low pressure high temperature stage. Okay, so this was all about this turbine and governor model. So we cannot stop here because we have to solve the generator model as well, because if you can see the transfer function, this block diagram is incomplete here. Okay, because from where we are getting this delta fs, obviously this delta fs is coming from where, from the generator output. Okay, from the generator output. So we will see how much delta fs will change, and this, and then we will draw the complete, because we have to draw here one more block. This is the governor turbine, then we will have the generator block, and the output of the generator is delta fs, that is given in the feedback to this loop. Then the whole speed load frequency control diagram will be completed. So for that, I will upload another video of around 20 or 25 or 30 minutes. Okay, thank you very much.